So yeah, good afternoon. So my name is Johannes Kühn. I'm working for Schneider-Kreuznach, and today I like to talk about a topic which is currently very high. So ruggedized lenses for harsh environments, especially for space applications. So just a quick overview. What we are talking about. Today we are talking about what is a ruggedized lens, and how can we make it, and how we can compare standard lenses and ruggedized lenses related to the special testing. And we will have a look at some real-world aerospace applications, and we will have a look at some future trends at the end, where we can see where we see the new space economy. So maybe some first words about myself. I've experienced over 16, 17 years now with Schneider-Kreuznach, ranging from production management to now technical sales. I changed the unit to industrial sales about 5 or 6 years ago. And so, yeah, today, high precision imaging isn't just for controlled laboratory settings. It's being deployed in satellites, engine diagnostics, and deep space missions. So what's the goal of Schneider? It's really simple. We like to provide the best optical solutions for the industry, ensuring that even the most extreme conditions and then your imaging system remains precise and reliable. Maybe a quick word on our heritage. Schneider-Kreuznach was founded for over 110 years ago in 1913. The headquarters is still here in Bad Kreuznach in Germany, and we have a global presence with offices from New York to Shenzhen, so worldwide. What are the main strategic business segments? We operate across several strategic segments, including photo, scene, and our business unit industry, which focuses on lenses and filters for possibly, of course, mission-critical applications. Inside the business unit industry, we are talking about standard lenses, standard filters, and of course about customized solution, semi-customized standard optics, and possibly about optical systems for measurement applications or calibrations of lenses and cameras. So now to the main topic. So what are ruggedized lenses? Essentially, they are high-performance optics designed to survive and function where standard lenses fail. While the optical design, so the glass itself, remains largely unchanged to ensure consistent image quality, the mechanical housing is completely, or sometimes only a little bit, re-engineered. That means we are using a robust metal housing and implement internal bonding of elements. This prevents the internal parts from loosening or shifting when exposed to intense mechanical stress. So what are the key features? As I said, we have often a very robust metal housing, and the key features include the fixed and glued mechanical components. Maybe you can share this with the laser pointer. On the right side, we have a standard lens, and you can see all the components inside. We have some optical elements, small mechanical elements like retaining rings. We have future mechanical parts, rear group and front group, and we have often aperture body with a lot of more mechanical small parts. And when we do a ruggedization of a lens, we are fixing all retaining rings inside the rear and the front group, and we glue the connections between the front group, the mechanical aperture body, and the rear group. So every mechanical part is fixed and secured with glue. So now we can compare the standard and the ruggedized lenses. So why can't we use often a standard lens? In a standard lens, vibration can cause elements to loosen, leading to a shift in the optical axis, possibly, and this results in a loss of calibration and a significant drop on image quality. So ruggedized lenses, on the other hand, offer higher durability and a stable focus under stress. This level of precision is essential for applications where every pixel counts, such as an autonomous system or satellite imaging. When we test our standard lenses and possibly our ruggedized lenses, reliability isn't just a claim, it's a proven fact through our special testing procedure. So our lenses undergo thermal cycling to ISO standards from about -25 degrees to +70 degrees. Here we run 5 test cycles, each lasting around 12 hours. Also, we perform humidity testing, simulating environments with up to 95% relative humidity where concentration is a real risk. So next testing is often shock tests and vibration tests. And for the ruggedized versions, especially, we conduct shock tests up to 100 G and vibration tests ranking from 10 to 500 Hertz with an acceleration of 2 G. And these tests ensure that when the lens is launched on a rocket, it arrives in orbit in a perfect working condition. Therefore, Schneider-Kreuznach is the original manufacturer of ruggedized lenses, and the company is well known for these lenses. And in addition to our extensive standard portfolio of ruggedized lenses, we can provide some more options like stabilized lenses. The difference here is the ruggedized lenses are engineered for survival. So these lenses are developed together with a really well-known space agency, and this technology is built to survive the violent vibrations and shock of a space launch. So as described before, we bond all mechanical components to ensure the physical stress, so no part inside of the lens can be loosened. When we are talking about stabilized lenses, these lenses are special engineered for precision. And they are originally developed for different special 3D measurement applications, for special industrial applications or medical applications. And this is about maintaining a stable optical focus, optical axis for accurate depth calculation. And when we look inside the lens, so all lens elements, not only the mechanical elements, are permanently fixed in the body. So this prevents the glass from shifting within the small gaps left by the tolerance in the mechanics, which would otherwise throw off the calibration. So now maybe I can talk about some special applications or other applications, not only space. So modern imaging systems often have to operate under extreme conditions, and especially in space missions. And in these environments, standard lenses frequently fail because they are not specially designed to withstand these high vibration, temperature changes, or mechanical stress. And so this creates a strong need for solutions that offer both, so not only precision, also reliability. So ruggedized lenses are specially engineered to meet all these requirements. Because of this durability, ruggedized lenses are used in a wide range of applications. We can talk about special industrial automation applications, possibly robotics, different machine vision applications, of course, traffic, railway inspection, and surveillance systems. And of course, now, a really growing segment is defense and aerospace technologies. So in summary, ruggedized lenses are essential for any system where failure is not an option and high performance imaging is required under extreme conditions. So now, as I said before, Schneider-Kreuznach is well known for ruggedized lenses, especially for space applications. And over the last 15 years, we sold about 5,000 lenses into special space applications or air applications worldwide to more than 50 customers. So actually I told something about some current space activities and special, of course, some use cases. So often lenses are used in satellites and CubeSats for imaging and Earth observation, and these technologies are used to monitor the Earth's surface, possibly the climate, disaster-stricken areas, or they could be used for military cases by capturing high-resolution images or video data, or of course live data. And we go to the possibly rocket launches, shuttles. These lenses or systems are often used to monitor the operation, to have a look at the engines, and that everything works well during the launch. Yes, in this case, the next two slides show some current space activities or launches where we were on board with some ruggedized standard Schneider lenses. I can show you some videos here. Here we can see a small video from the launch of the Artemis II with the onboard camera on the outside. The camera is looking down to watch the separation of the boosters. And here we are around 2 minutes after the start. You see a clear image and everything worked well. The next video is around 5 years ago. It shows the separation of the James Webb Telescope from the Ariane 5 rocket in December 2021. This was after around 20 minutes after the start and around 1,400 kilometers distance from the Earth. So I think we talked already about the environmental space changes, challenges. And yeah, often at the launch, we have really high shock and vibrations when we're going higher and higher to low orbit or to geo orbit, possibly. We have thermal cycling, vacuum problems. Of course, mechanical stress is high on the optical systems, So there's often a risk of misalignment and possibly of drift of the focus. We have to talk about a little bit about here radiation protection, about dust, moisture, and pressure changes, and there's often a need of really small lenses and very low light lenses. So we come to a point to see that sometimes only a ruggedization is not enough. So possibly we need some more changes in our standard lenses to fulfill the customer's requirements. What we see on the left side, we see standard lens, and on the right side, we see the same lens, the same optical elements, but they are put or assembled into special, smaller housing. So to meet all of these space challenges, we modify our standard products. This possibly could include to use a fixed iris, a single mechanical body. We are able to reduce the total number of parts to make the housing more compact and robust. And we are able to optimize these lenses possibly to infinity. Sometimes it is possible. And yes, as I said, we assemble them as light as possible to meet the strict wide requirements of the space flight. Yeah, now short summary and maybe some future trends. Looking ahead, the new space economy and higher launch cadences are driving a shift towards even higher robustness. We see a strong trend towards tighter integration with AI-based imaging and a massive demand for autonomous systems, maybe like drones, becoming more and more. So in conclusion, ruggedized lenses are essential for mission-critical systems where failure is not an option. So our designs are validated under real mission conditions, ensuring high-performance imaging in the hardest environments on and off the planet. So thank you very much for your attention. And yeah, I'm happy now to take any questions you may have. And otherwise, you can contact me or us from Schneider-Kreuznach directly later.
Johannes, thank you for the presentation. And I have a question. Where's the limit for lenses at the moment?
Again,
looking at temperature or something, where would you say is a limit that's not possible to use lenses anymore? Shock or temperature, pressure?
I think it's really hard to say. So we know from validated qualifications that our lens could be used between minus 50 degree up to 80 degree. But we are not able to test it, but we know from the application that the lenses are still working in this range. So it's of course possible. So what I have shown in my presentation are only the standard environmental tests. So I think often the customer's requirements are often higher and normally our lenses will fulfill all the requirements.
Thank you.